Okay, let's start. So today we have our own Professor Paul Sandick. Paul got a bachelor's degree in mathematics at New York University and a PhD in physics at the University of Minnesota. And then she went to UT Austin for postdoc fellow position before he joined the department. She moved to the department 2 years ago, and her studies in particle physics, especially things related to dark matter. So she will tell us more details on that.
Okay. All right, thanks, guys. And there are a couple more seats in front if anybody wants to scoot up very close. So I debated about my title because I wasn't sure if I wanted to scare people away or not. But I'm going to tell you about advances in dark matter phenomenology and a lot about what I've been doing and what people in my group have been doing the last 2 years that I've been here. So I could have put the word supersymmetry in the title, but I did not. OK, so when I gave my job talk here exactly 2.5 years plus 2 days ago, I started with this slide, which is the matter inventory of the universe. And unsurprisingly, things haven't changed that much. Still, we only know about 15 or 16% of the matter in the universe is the stuff that we're made of and the stuff that stars is made of and gas and all that stuff that we understand, particles in the standard model. But the vast majority of the stuff in the universe is stuff that we don't understand. And so I'm going to start with some things that are not advances, some very old background on dark matter, and then I'll lead up to what is new. OK, so this was not the first evidence of dark matter, but it's probably the easiest to understand. This is something you can explain to your 5-year-old cousin. But this was the galaxy scale evidence for dark matter was discovered by Vera Rubin and her collaborators in the 60s and 70s. And the idea was that they were just looking at galaxies and looking how stuff rotates around galaxies, like bodies that are sort of near the edge of the galaxy. And this is a problem in Newtonian dynamics, right? So if you know, if the visible matter is all the stuff that's there, then you can sort of estimate how much there is by looking at it, right? Because it emits light. And the gravitational attraction of any body that's causing it to rotate is just due to the gravitational force of all that visible matter, if that's all the stuff there is. And so you can calculate the rotational velocity, and it's the square root of Newton's gravitational constant times the mass contained within that radius r divided by the radius itself. And so if you go very far away from this thing, outside of the distribution of visible matter, if that's all the stuff there is, then m of r should be constant. And the rotational velocity should fall off like 1 over the square root of r. So that's the story. And people went out and measured this. And this is the rotational velocity as a function of radius for a particular galaxy. And you can see that the data don't look at all like they fall off like 1 over root r. So you can see there's the prediction for the stuff, the visible matter that's in the disk and the gas. And those things do not make up enough stuff to account for this flat rotational curve. So there's a way to reconcile this. And that is by adding a dark matter halo component to propose that this object exists in a big halo of dark matter that extends beyond the visible matter. And we don't see it, but m of r is indeed not constant out there. OK, yeah?
One question. How do you measure this velocity? I mean, 100 kilometers per second on the size scale of galaxies. And
yeah.
I think one cycle is 200 million years for the Milky Way or something like this. You see a static picture, how do you measure a velocity?
My guess is you're measuring some Doppler shift, but maybe Anil has, yes? OK, that's right.
Okay.
Yeah. And that's actually what they do with the cluster scale evidence as well. So the very first evidence of dark matter actually wasn't on galaxy scales, but it was on cluster scales, so clusters of galaxies, much larger objects. And the idea here is it's pretty similar, right? We have this virial theorem that tells us that the average kinetic energy is related to the average gravitational potential energy of this gravitationally bound system. And so this stuff is related in some way to the total mass of the system. And you can get an idea of what the total kinetic energy of the system is by measuring the motion of objects at the edge. And you do that with the Doppler shift. And so this is the coma cluster, actually the system that he did these measurements on back in the 1930s. And what he found is that if you just use this equation, the velocities that you're measuring imply that there's a lot more mass in this cluster of galaxies than just the stuff that's visible. And so he wrote in 1933, if this overdensity is confirmed, we would arrive at the astonishing conclusion that dark matter is present with a much greater density than luminous matter. Dead on, 1933. So now, 80 years into the future, we have a lot more I don't know, interesting, exciting, fun, technical ways to measure things about dark matter. And so this is a picture that I always like to show because it's very clear what's going on here. So this is the bullet cluster of galaxies, another galaxy cluster, but this is actually two galaxy clusters having a head-on collision. And so you can see these things that look like stars, but they're actually galaxies, are measured in optical. And then galaxy clusters, actually, the most massive component in galaxy clusters isn't the galaxies themselves. It's the gas that surrounds and goes in between the galaxies. And so X-ray measurements actually tell you where that gas is. And so on this same picture now, they've superposed some measurements from the Chandra X-ray Observatory, and that's this in the reddish color. That's where all of the hot gas is. And you can see a little bit of something that looks like a shock here, and all the gas is kind of concentrated in the middle, because the gas would interact with the gas from the opposite cluster electromagnetically as well, so it would get slowed down in the center. Whereas the galaxies themselves would just fly right through. And so you can see sort of hints of a cluster of galaxies here and a cluster of galaxies here. Now, if there were no dark matter, then the hot gas would make up most of the mass of this cluster. And so weak gravitational lensing would tell you where the mass distribution is, like where most of the mass is. And that should lie on top of the hot gas. But it doesn't. Weak gravitational lensing shows you that most of the mass in the clusters is tracking the motion of the galaxies themselves. So it's something else that interacts only gravitationally. Now this is really important because modified gravity could explain some of the things that we think we don't understand about how bodies rotate around each other and things like that. But modified gravity cannot explain this. You definitely need at least a dark matter component in order to explain this observation. And this isn't the only cluster picture in which things like this happen. There are tens probably of pictures that are understood, perhaps not this well, but where the same kind of dynamics is happening. Okay, so fast forward, there's lots more pieces of evidence, but I'm not going to go through all of them. Here's sort of the catalog of things that we know about dark matter. We certainly know that some explanation is necessary for the observed gravitational phenomena, and all of those phenomena that we have observed are purely gravitational. But we do know that dark matter is not made of standard model particles. We say that it's non-baryonic. Because if it were made of baryonic matter, the same stuff that we're made of, then there would have been more baryons around when the first elements were forming. And we know from Big Bang nucleosynthesis how much baryons we expected to be around then. Seems to agree with all of our other measurements of how much baryons are around. So we know that dark matter is something new. We also know from the cosmic microwave background measurements exactly how much there is. Yeah?
Gravitational, I mean, it has the same gravitational properties as our regular matter.
Yeah. Yes, it does. Yeah, so we know from the cosmic microwave background pretty much exactly how much of this stuff there is in the universe. And here, omega is sort of shorthand for saying what fraction of the energy of the universe it makes up. We know that it is not electrically charged, otherwise it would have formed bound states with regular matter, and those haven't been observed. It has to be stable, or at least long-lived enough that we're still observing it today, right? We can actively observe the dark matter that is around today, gravitationally. So it's still around today. And it's slow-moving. We say that it's cold because it had to have been very slow-moving at structure formation because it helped structures clump together. If it were very fast-moving, like neutrinos, which are almost massless, but not quite, if it were very fast-moving, it would have dragged those structures apart. Instead, this provided the seeds for structure formation. Okay, so then you write down your laundry list of what it could be, and this is sort of the shorthand laundry list. Standard matter particles, no way. New dark matter particles that you invent just to solve the dark matter problem, yeah, that's a possibility, right? It could be that the only purpose these new particles have in life is just to explain the dark matter. Or there are lots of extensions of the standard model where new particles appear that could actually explain the dark matter too. And in some cases, they appear very naturally. I find this second explanation much more compelling, but of course, that doesn't mean that it's the right explanation. Okay, so one thing that you need to keep in mind when you're talking about inventing new standard model extensions is that any new extension of the standard model or any new theory of particle physics should do two things at the very least. It should contain the standard model and the experimental results to date, because so far everything we've observed, all particle physics experiments seem to be in agreement with the standard model to first order. But furthermore, it's better if it solves at least some of the other outstanding problems in particle physics. Just because the Higgs boson has been discovered doesn't mean that particle physics has been done. There are still lots of other interesting questions. And so ideally, a new theory of particle physics should really do both of these things. Okay, so regardless of where your dark matter particle came from, let's assume you have a new particle that explains the dark matter, right? So if you propose some new particle, you want to know how much of it is still around in the universe today. And so you can go through this sort of experiment in your mind. where you postulate there's this new heavy particle in the early universe. And in the very early universe, when everything was super hot, this was in thermal equilibrium. So two of these new particles, which I'll call chi, could annihilate with each other and produce standard model particles. It's very hot, so standard model particles can annihilate with each other and produce dark matter particles. And so you have sort of a fixed equilibrium value of how much of this stuff there is. But as the universe expands and cools, things begin to change. So the first thing that happens is that the universe cools to the point where two dark matter particles, because they're heavier than the standard model stuff, still can annihilate and produce standard model particles. But now standard model particles no longer have enough energy to combine with each other, to interact with each other, to produce two heavier dark matter particles. And so at this point, the number density of dark matter particles would start to decrease. And so what you're looking at here is the co-moving number density as a function of, you can think of this as time moving to the right. And so now we're in this region 2, where the abundance of dark matter particles is just decreasing. Now, the third thing that happens is where that expansion takes over, or becomes the dominant effect. And so in this last sort of era, which happened a really long time ago, these dark matter particles now are having trouble finding each other to annihilate. So the universe is expanding, and dark matter particles can no longer find each other to annihilate. And so it's this last stage here, 3, where expansion and annihilation are competing to determine the number density. And so you can solve the Boltzmann equation to find out how much is left today. And you can see the Hubble constant here, or not constant, but the Hubble parameter tells you about the expansion rate of the universe, and it's competing with the annihilation rate of dark matter particles. So the larger the annihilation rate, the sigma v, the more dark matter particles are going to annihilate with each other. And so increasing the annihilation cross-section will decrease the number density today.
When you write this Boltzmann equation, do you assume they're like fermions, bosons, or?
We have no assumption in here yet.
But this goes into the collision integral, right?
Yeah.
So, presumably they have to collide to do stuff.
That's all taken care of in the annihilation cross-section. You're just talking about equilibrium number densities.
Oh, okay. So they just behave as classical.
Yeah. Okay. Right. So the interesting thing that happens here is that if you look at this equation and you solve it numerically, what you find is that if these particles are stable and they have masses in the GeV to TeV range and cross sections that are sort of roughly at the weak scale, that's one of the 4 fundamental forces, the weak nuclear scale, then you get approximately the right relic abundance of WIMP dark matter today. And so we call this the WIMP coincidence for weakly interacting massive particles, or some people call it the WIMP miracle. But nonetheless, this is an interesting thing. It could be telling us that the weak scale is important in cosmology. We already know that the weak scale is important in particle physics. So it's unclear how we should take this, but it's certainly an interesting thing that bears looking into. So if we go back to what we know, none of this stuff indicated what scale these particle masses should be at, right? None of this tells us that we should be looking at weakly interacting massive particles. So I want to emphasize that we do not know that dark matter is made of weakly interacting massive particles, or WIMPs. But because of this coincidence, the fact that the weak scale is important in particle physics and appears naturally in new theories of particle physics, and also this WIMP coincidence of the relic abundance, it does bear looking into. Okay, so assuming WIMPs are what makes up the dark matter, we have to figure out how to determine that that is a true statement, right? So there are 3 detection strategies. The first is colliders. So particle colliders collide standard model particles and produce stuff that maybe is not standard model particles. So the idea here is you can collide 2 standard model particles, produce maybe 2 dark matter particles, and we still don't care whether it's a fermion or a boson. And here, since you're producing WIMPs, these guys interact very weakly, and so you won't observe them in the detector. So you'll be looking for a missing energy signature primarily. Or if you have a dark matter particle that fits into a bigger theory of particle physics, you can try to identify some of the other particles in that theory and maybe look at the decays of the next to lightest particles, because again, eventually they'll decay down into something that flies out of the detector, the dark matter particle. Okay, so a second detection strategy is called direct detection, and the idea here is to observe WIMPs directly through scattering with nuclei in terrestrial detectors. I'll talk more about that a little bit later. And also indirect detection. So indirect detection is sort of the inverse of the collider problem here. And it's actually the same thing that happened in the early universe. So dark matter is around to some extent, it should still be annihilating if it annihilated in the early universe. And so you can look for the products of the WIMP annihilation or decay. And those, the experiments that search for those are located on Earth or also in satellites. So these are the cartoon version, and I'm going to draw you another cartoon version, but it's a slightly more physics-related cartoon version. And that looks like this. So basically, you have two dark matter particles and two standard model particles. They can interact in a variety of ways. Until we figure out what the new physics is, we don't know exactly how they interact. But you can try to put limits on how this happens. And so if you just look at this diagram in different directions, first I'm going to talk about direct detection. Then I'll talk about indirect detection, which is the same process that happened in the early universe, that annihilation. And finally, I'll talk about collider searches, which go the opposite way. OK, so direct detection. The idea here basically is that we live in a halo of WIMPs, because we live in a galaxy. And as I showed you with those rotation curves, galaxies are embedded in halos of dark matter particles at the very least. And so if these WIMPs are all around us, then occasionally they're going to bump into nuclei. And there was actually a paper written, co-authored by one of my postdocs, Chris Savage, who I'm not sure if he's here, about how often that happens, how often WIMPs would collide with actually us in our bodies, which is kind of amusing. But here's how this works. So a dark matter particle, which I'm going to continue to call chi, or a neutron actually acts the same, tends to scatter on the nucleus of whatever your detector material is. And when that happens, I should say, for a dark matter particle with a mass of 100 GeV, so near the Higgs mass, the recoil energy that you should be looking for is like tens of keV. So it's a pretty small energy. It's not very easy to measure. But the idea is basically to reduce the backgrounds. So neutrons are one background, and those are tricky. But the vastly more present backgrounds are other things, like photons or betas or alphas. But these things all tend to scatter on the electrons in the detector material. And so to be able to distinguish electron recoils from nuclear recoils is the main game. And so the way that you can do that is by looking at what the scatterings produce. These colors are not totally coded correctly here. But things that scatter on electrons tend to produce more ionization and scintillation, and things that scatter on nuclei tend to produce more heat in the detector. But if you look at how detectors are looking to try to reduce their backgrounds, one of the primary ways is to measure more than one of these three things. If you measure two of those three things, then you can look at the ratios and that gives you a much better handle on whether it's an electron scatter or a nuclear scatter. So the big question, though, is how occasionally does this happen? If it's going to happen, in a detector the size of this room once every million years, then it's probably not worth building a detector, right? And so you want to calculate the rate that you expect this to happen. And the differential rate here is given in counts in the detector per ton of detector material per year per keV. So you can tell by the units that this is not something that's going to be happening like hundreds of times a day. But the way this is calculated is basically just by looking at the flux of WIMPs. So that's the number density of WIMPs times the velocity, averaged over some velocity distribution. And then you have to worry about the particle physics part, which depends on the WIMP nuclear cross-section here. So the larger the WIMP nuclear cross-section, the more often this is going to happen in the detector. OK, so there are tons of experiments looking for this. And I'm not even sure if this is a complete list of all of the experiments that are active right now. But you can see this is like a substantial worldwide effort all the way across the map. One thing to note is that there is only one experiment in the South Pole, and that's actually still sort of in the R&D phase. They've deployed sort of the test module, but they're not taking actual WIMP data yet. So everybody else is in the northern hemisphere. And here is the current status. And I'm only showing the low mass region. But the current status is more or less that all of these shaded regions are regions where there is a potential signal. And all of the curves are exclusion contours. So you're looking at the WIMP nucleon cross-section, in square centimeters here or picobarns on the right-hand side, as a function of WIMP mass. And you can see that, for example, these DAMA regions, there's a signal observed that could be compatible with either of these two regions, are both excluded by the solid blue contour, which is a CDMS, the CDMS experiment. CDMS actually has a more strong constraint, this red dashed one. The constraints from liquefied noble gases, such as xenon 100, are currently the most stringent, which basically exclude all of these regions that are favored because there are some excess events there. So to give you an example, this blue shaded region here is the most recent. And this came from the CDMS-2 experiment. They observed 3 events in their detector over the period of the WIMP search, and they expected 0.7. So one thing I should say is that all of these experiments, except for DAMA, that are listed here, oh, and actually Cogent, most of these experiments are what are called zero background experiments. That means that they understand and reduce their backgrounds to the extent that they expect less than 1 background event. So basically then, any event that you see, you have some probability of attributing to a WIMP. So they expected 0.7 background events. They observed 3, which if you do the likelihood analysis, that's a 0.19% probability for the background-only hypothesis. What do we make of that? It's not really clear yet, right? So there are more experiments. CDMS themselves have constructed a CDMS light detector that is going to have a lower threshold, and so hopefully it'll come down here. And it'll either see more events, or it will eliminate this as a WIMP signal.
Earl?
Yeah.
So this is a fairly range window for cross sections, just orders of magnitude.
Yeah.
And given that we know
Very little.
not much about
So everything above here is excluded, right? Oh, so these are, right, because if the cross-section were any larger than this, we would have seen screaming signals in lots of detectors by now. So everything above these contours, and I think maybe the most reasonable thing to do is just sort of put a diagonal line in this plane and say, certainly everything above there, we would have seen screaming signals by now. And anything below there, there are certainly models that predict cross-sections down here. And I'll show you some of them later. Those are not yet excluded.
Well, do you have any idea how many events CMS would have expected under some perfunctory density model, like a standard profile, over their runtime?
How many they would have expected if you like really mess with the velocity distribution, you mean? Or?
I mean, given some standard profile and their exposure.
Oh, how many WIMP events?
Yeah.
Yeah, so that's what this region is. This is the region that's compatible with 3 events under the standard halo model assumption. Okay, so that's all I'm going to say about direct detection for now, because I'm going to come back to that later. Indirect detection, the idea here is basically the same thing that happened in the early universe should still be happening today. Now, I'm going to talk mostly about annihilation, but there are certainly models where the dark matter particles are not stable, and so they decay, and they just happen to be decaying right now. I find stability a more compelling answer, but who knows? But the idea here is that's nice is that basically anywhere where you have a good collection of dark matter, this should be happening, right? And there are lots of experiments looking for these annihilation and decay products, or experiments that are designed to look for other things that would be sensitive to these. However, you're looking for this annihilation and decay maybe in our galaxy, maybe near the galactic center. Astrophysics can be very complicated, and there are lots of things that we don't understand that would make it very problematic to extract a strong WIMP signal from the data at this point. Okay, so as I said, you need a lot of dark matter. So you could look at a large region of space, like look at all of the dark matter annihilation signal that would be coming from the entire Milky Way halo. And here I've put sort of the seminal references and then also work that I've done that's related to this. Other options are you could look at where there's a strong concentration of dark matter. So the dark matter density should be the largest near the galactic center. So if you look directly towards the Milky Way galactic center, you should get a strong dark matter signal. Unfortunately, the galactic center is a super complicated place. And so extracting the backgrounds or extracting a signal from the backgrounds would be really difficult. Other prospects are to look at dwarf galaxies, specifically like dwarf spheroidal galaxies are really dark matter dominated objects. And so it's easy to extract a signal if there is some excess of gamma rays coming from a dwarf spheroidal galaxy. Or you could look at sort of more generic Milky Way substructure modeling to see if there's any possibility for a signal there. And finally, in the sun or the Earth, if dark matter scatters on nuclei and collects there, then there would be a collection of dark matter, and dark matter would be annihilating. And so there's some possibility to see neutrinos coming from the sun or the Earth where dark matter may have collected. In any case, the way that this would work, and it says supersymmetric neutralinos, that is not necessary. This is a generic WIMP particle annihilating, and from this annihilation comes stuff, standard model particles. And we don't know what those are, but whatever they are, they're going to hadronize or decay, and at the end of the day, you will always end up with a collection of stable standard model particles. And so that could be electrons and positrons, neutrinos, protons, antiprotons, who knows, and certainly photons belong in this list. And so then you try to look for these things and see if you see an excess coming from any of those locations. Now, there is so much to talk about with indirect detection that I'm not going to go through very much of it. I will say there are 2 interesting results from the last year. One is the confirmation of the rising positron fraction by the alpha magnetic spectrometer, the AMS experiment. So the positron fraction is the flux of positrons relative to the flux of electrons plus positrons. Okay. Positrons are antimatter, right? So they are produced primarily in cosmic ray collisions. And the cosmic ray spectrum falls with energy, so you would expect that the flux of positrons should fall with energy also. So what you expect is that it looks like this. Unfortunately, or maybe fortunately, interestingly, it doesn't look like that at all. And we had hints of this. It was measured in 2009 by Pamela, and everybody went crazy saying it could be dark matter. And then the Fermi satellite figured out how they could measure it, even though they don't even have magnets on board, but it was so interesting that they put a lot of work into that. And now the alpha magnetic spectrometer has measured it, and it does indeed continue rising. So is it dark matter? Maybe, probably not, in my opinion, just because of the contrived model you would need to create something like this. And also, there are these things called pulsars, which are known to produce large fluxes of positrons. So it's really not clear, and furthermore, a question here is how would you ever distinguish a pulsar source from a dark matter source? So this could end up being a very important part of the puzzle if a similar dark matter signal or a complementary dark matter signal is observed elsewhere, but for the moment, I'm going to table it. The other one is the gamma ray line, and we had a colloquium from Christoph Venegar last year, so I'm not going to say too much about this, except that the Fermi Large Area Telescope observed an excess of photons at 130 GeV. And if we call that a line signal, which is seen to be a smoking gun of dark matter, because there aren't that many astrophysical ways. In fact, there are pretty much 0 ways that you can astrophysically produce a bunch of photons at exactly one energy, that energy being 130 GeV for sure. So it's an interesting thing. It's not clear whether it's a dark matter signal or whether it's a systematic. My money is on systematic at this point because when Fermi looks at the Earth's sort of limb, like the outer region of the Earth, they see the signal coming from there too. And there should be no reason why there's an excess of dark matter hovering around the Earth. So bit bizarre. We don't know what it is yet, but this line search is a really important search strategy for dark matter. And so I'm not going to talk any more about it, but I did write a paper recently trying to answer the question of if the MSSM, the minimal supersymmetric standard model, is the scenario that describes the universe, then would it be possible to see a line signal without a continuum signal, or would you only see a continuum photon signal before you see a line signal? And so that's an interesting question, but I won't dwell on it.
Sorry.
Yes?
What was the bottom panel on the right-hand side? I don't understand.
Oh, I think that's just the residuals. So like, that's the residuals with respect to this model that so this is an NFW halo profile, dark matter of 133 GeV, I guess. And this is
the residuals against that solid line.
the residuals against the dark matter model, right?
Okay.
So that's showing that this dark matter model actually is a good explanation for the line.
And then that 4.1 sigma is the gray relative to the dotted.
Yeah, I think so. Yeah, so it's a 4.1 sigma local significance, but when you take into account all of who knows what, it ends up being like a 2 sigma thing. Okay, so that's all I'm going to say about indirect detection. But the thing that I want you to keep remembering is that even though this is messy and awful and strange and there are all these interesting results, the reason that it's so important is because this is the search strategy that relates directly back to what happened in the early universe and that annihilation rate. That's not to say that it has to. There are plenty of models of dark matter where the annihilation in the early universe is completely different than the annihilation today, but there is a possibility of a link here, which makes this a really important search strategy to actually nail down that the thing that is making this signal is the same thing that annihilated in the early universe. Okay, so I'm just going to I have one short slide on the LHC, and the reason that I chose this is because these, what are called mono-anything searches, are really exciting right now. And so the idea here, you can see your familiar diagram, right? We have 2 standard model particles producing 2 dark matter particles. And this is what's happening in the LHC. You have a quark and an anti-quark collide. At the end of the day, you have 2 dark matter particles which don't interact in the detector, so you will never see these things. And so I said missing energy searches, but those searches are very difficult and not the most promising way to look for this stuff. However, what will happen is that you will have initial state radiation. So off of one of these quarks, you will radiate a gluon or a photon or a W or Z boson. And so if you look for events where you have one of these things, so a gluon would look like a jet, but where you have one of these things, then you can see if there's any excess of those relative to what you would expect if this process with dark matter in the final state never happens. So if you know what the new physics is, then you just sit down and you calculate the rate at which this would happen, and you compare it to the rate at which a standard model process would happen to produce a mono something. However, we don't know what this new physics is, right? So if you have a model, you can easily calculate it. If you don't, then one of the things that's popular right now is to do this effective operator analysis. And so basically, the D means that we have assumed that we're talking about a Dirac fermion for the dark matter. And then you write down all of the possible operators that could be involved here, right? And so then you take one of them. So we'll pick D5. And each of them comes with some characteristic mass scale coefficient, right? So if you pick one of these operators and you say, that is the only thing that is doing this process, what limit can I put on the mass scale associated with that process? And if that's the only thing, the only way that dark matter can interact with quarks, then you can also relate that to dark matter scattering on quarks in a direct detection experiment. Okay, so this is what is done here. So you have a limit on this mass scale, right? The mass scale has to be above this solid blue line. And just for reference, if this were the only process in the early universe as well, this green line is what you would expect that mass scale to be for a thermal relic, for that freeze-out mechanism. And you can also put a limit on the annihilation cross-section here. Okay. So interesting, but you have to know what the theory of, you either have to know what the theory of physics is, or you have to assume that only one operator is responsible for it. So let's go back to this. Interesting new theories of particle physics. So I'm going to tell you about one interesting theory of particle physics, which is my favorite, which is supersymmetry. So supersymmetry is a symmetry between fermions and bosons. And basically, one of the biggest reasons that I think supersymmetry is so important is because it is the only possible extension of the Poincare algebra, that is the standard space-time symmetries, in a consistent four-dimensional quantum field theory. And this was a theorem by Haug, Gluck-Blazensky, and Sonius from 1975. The practical consequence of the symmetry between fermions and bosons is that each standard model particle has to have a supersymmetric partner. Okay, so we take the standard model and we make a copy of it. And so you have all of the quarks, all of the leptons, which include electrons, muons, and taus, and the associated neutrinos. And then you also have the gauge bosons. Okay, so we make a copy of it. Instead of quarks, we now have scalar particles, which we call squarks, and they're denoted with a tilde. Instead of the leptons, we now have scalar leptons, so, which we call sleptons. So these green and purple ones are all fermions, and now we have these scalar particles. So these are 3 generations of matter scalars, or matter fermions. Now the gauge bosons. They're a little bit more complicated. So the gluon becomes the gluino, and because these are fermions, we put ino at the end of the name, so gluon becomes gluino. These guys, electroweak symmetry breaking is going to mess with a lot. And so what we call them are the neutralinos and the chargino. And so we call those guys the gauginos, if you want. And then finally, we have our Higgs sector. Now, in the standard model, you only need 1 Higgs doublet. But in supersymmetry, you need 2 Higgs doublets. So our Higgs sector is a little bit larger than normal. And the associated Higgs particles are scalar particles, and so we have fermionic Higgsinos. And there's 1 charged one and 2 neutral ones. Okay, so the charged guys are charginos, and the neutral guys are neutralinos. And it is the lightest neutralino that is our dark matter candidate.
What happens to the photon?
Well, so a while ago, when everybody thought well, I guess when the photon itself was thought to be, its partner was thought to be the lightest supersymmetric particle, it was called the photino. But actually now what we have is, it's sort of like before electroweak symmetry breaks it to a photon and the W and the Z, we have the W, the B, and the Higgsino. But so we call it the Bino and the Wino instead of the photino. But they're hidden here in these guys. They're admixtures.
That's helpful.
Okay, so one thing we know about supersymmetry is that it has to be broken. It can't be an exact symmetry of nature because we would have long ago seen 511 keV selectrons, right? So what I just showed you was the minimal supersymmetric standard model, the minimal particle content possible in a supersymmetric theory. And even there, depending on how you count with CP violation or whatever, you have definitely more than 100 free parameters to define the theory, which seems awful, right? That is an awful, awful way to go about things. So there are a variety of reasons why you should think that something more simple is at play. And one, we call this unification or structure, but one reason that something more simple, some simplifying principle should be at play, is that these supersymmetric theories predict the gauge couplings to unify, the gauge couplings of the standard model to unify at a high scale. And in a completely unstructured theory, it's wrong. It shouldn't give you that, right? You should, if the gauge couplings unify at a high scale, there should be some structure to a theory that makes that happen. That's a personal thought. But there are other practical reasons, like the suppression of flavor-changing neutral currents or Kaon, anti-Kaon oscillations, or who knows what. But there are lots of things that are not observed that indicate that there is some structure to the theory that prevents those things from happening. So sort of the canonical supersymmetric theory that everyone talks about is called the constrained MSSM, or the CMSSM. And this has been reduced down to 4 parameters and a sign. So if I show you all of the terms that you can add to the supersymmetric Lagrangian for soft breaking, so these are terms that don't destroy cancellations of quadratic divergences. These are all the possible terms you can have. And the CMSSM has 4 parameters. So one is the gaugino mass. It's a universal mass at a high scale for all of the gauginos. And so that's this term here. There's a universal mass for all the scalars. This term here, a universal mass for all the trilinear couplings. That means terms that have 3 scalar particles, like these 3 terms here. There's a universal value for that coupling that sits in front of it. A value for the ratio of the Higgs vacuum expectation values, and the sign of this thing called mu, which is the Higgs mixing parameter, or it's the coefficient of the Higgs bilinear term. Okay, all of that aside, the important thing that I want you to remember from this is M1/2, because this is the universal gaugino mass, and it determines the mass of the BINO, WINO, and gluino. The BINO and WINO are super important because those are neutralinos, and they're potentially dark matter candidates. So here's what that looks like when you put this into your theory at a high scale. So this is the running mass as a function of energy. We and the LHC live down here along the left side. And so what we would observe is a spectrum of particles. And we get that by assuming that, say, all of the gauginos are universal at this high scale. And then they use the renormalization group equations to get out the low scale particle content and all the rest of the phenomenology. So I just want to emphasize again, we have the BINO, which is the lightest, which is always going to happen if you have a universal gaugino mass. And then we have the WINO, and these are labeled M1, M2, and M3 by their standard model gauge groups. And then the gluino is up there, and the gluino just sort of sits by itself. We don't have to worry about it. The CMSSM also has a universal value for the scalar mass, and the Higgs, these are the effective Higgs masses. And see, this guy running negative means that electroweak symmetry has been broken, which is very good. But that all happens naturally in supersymmetry. And I want to point out that these are not just universal at any scale. They're universal at the scale at which the gauge couplings unify. So this is a thing that is chosen. It doesn't necessarily have to be that way. OK, 2 new things have happened that are going to be important when we look at the phenomenology of this model that I've just described. One is that the Higgs boson was discovered. So I'm actually just telling you about the standard model Higgs boson right now, because we don't know what kind of Higgs boson has been discovered. But if we assume that it's just a standard model Higgs boson, then the standard model Higgs potential is super simple. Phi here is the Higgs field. And there are 2 coefficients. There are 2 free parameters. But in fact, we know that the Higgs potential is related to the masses of the W and the Z, and we know the masses of the W and the Z. So that eliminates one of these parameters. And so we're left with one more parameter. And that new parameter in the Higgs potential is the Higgs mass. So once you know the Higgs mass, you can calculate anything. And so this is the Higgs production cross-sections as a function of Higgs mass before we knew what the Higgs mass was. And this is the Higgs branching ratios, what the Higgs decays to as a function of Higgs mass. And so now we live on one line at 126 GeV in these planes. And so when people say this, the Higgs is standard model like, this is what they mean. So Atlas goes out and measures what the Higgs decays to. And if it were exactly what was predicted in the standard model with this one free parameter, then you would find the ratios that are predicted by this plot. And that would be at +1 here in terms of what they call signal strength. And most of these branching ratios sort of agree with that. There's some deviation. And what, of course, everyone who does beyond the standard model physics hopes is that this deviation ends up being strong enough that it does not look like a standard model Higgs anymore. But so far, it kind of looks like a standard model Higgs. But certainly, it was discovered, and we know what its mass is. OK, the other important thing is the branching ratio of beta mu mu. So this decay of a B sub s meson, which is an anti-B quark and an S quark, decaying to 2 muons is something that is super, super rare in the standard model. It's a loop process, and it goes through these 2 diagrams here, which you don't have to understand the details. Just notice that there's a loop here, and that means this process is super, super rare. Now, in the standard model, really, these are the only two significant ways that that can happen. But if you have any new particles in your theory, new particles can make new particle loops. And that can make new ways that this decay can happen, which means that you would expect it to happen more, or actually these diagrams can even interfere. You would expect it to happen a different fraction of the time than you would if it were just the standard model. So this had always been, I mean, this has been known for a long time, and people would always predict, like, in my theory of new physics, here's the contribution to this decay. And it had never been measured. There were only just limits on how large this branching ratio can be. But it was finally measured by LHCb this year. And so this red curve here is the standard model prediction for the branching ratio of beta mu mu. And the data do indicate that it is consistent with the standard model. The errors here, though, on this branching ratio are large enough that it is still consistent with lots and lots of models of new physics. So this is a thing that we all have to keep in mind. It's very important, but it's not a game killer. OK, so now I'm going to go to the new stuff, specifically stuff that I've worked on. So I'm going to talk about two sort of things that go beyond the CMSSM, because as I'll show you, it's becoming clear that the CMSSM is not good enough anymore. So I'll talk about two things that go beyond, and then I'll talk about also direct detection and dark matter tuning. I'll explain what that means in a minute, and also looking forward to some analyses that are going to happen in the very near future and what we can expect from those. OK, so going back to this picture, this is the old standard CMSSM. And here is what it looks like to me. So we've fixed some of the parameters, like tangent beta. And the two really relevant, phenomenologically relevant parameters here are the universal scalar mass and universal gaugino mass. So if you go to the upper right of this plot, all the particles become very heavy. If you go to the lower left, all the particles become very light. So there are lots of constraints in this plane. First of all, this brown region is excluded because the charged tau, the partner of the tau lepton, is the lightest supersymmetric particle. Charged dark matter is no good. Then there is this black dashed contour. Everything to the left of that is excluded because the LEP would have copiously produced charginos, and they didn't. There is a pink shaded region which is actually favored by the measurement of the muon anomalous magnetic moment, which seems to disagree with the standard model prediction. And so in this region, you could explain that. It's not clear how seriously you want to take that as a signal of new physics, because not all measurements agree on it. But it's an interesting thing to plot. There's also a green region which is excluded because it would predict too much B decay into S gamma. These are B quarks and S quarks. OK. Actually, before I get to that, there are a few other things. So there are contours of the Higgs mass, and you can see the Higgs mass is too small everywhere here, like by a lot, 119 GeV all the way over on the right side of this plot. And there's also the current LHC limit. Everything to the left of that contour is excluded because squarks and gluinos would have been produced at the LHC. So basically, all the interesting stuff is happening to the left of the LHC line, and the LHC says it's not there. Now, there's one more interesting thing, and that is this blue dark contour, which is actually a shaded region, which is where this model predicts exactly the right amount of dark matter. So that's really cool. And there's actually still some space there where it predicts exactly the right amount of dark matter, where the LHC has not excluded it, but the Higgs mass is too small. I should say this region is called the co-annihilation strip because neutralinos and staus have nearly the same mass. And so this process here, neutralino and stau going to something, is very efficient, and that brings the relic abundance down. Otherwise, there is just too much dark matter. So in all the rest of this white space here, there's too much dark matter in this model, which would overclose the universe. This is also no good. OK, so in the CMSSM, and what I just showed you, and this is generally true in the MSSM, it's typical that the abundance of neutralinos is too big. And so some mechanism is necessary to make the abundance of neutralinos what we observe in dark matter. And those mechanisms are co-annihilations. That could be co-annihilations with staus or stops or charginos, anything. It also could be pole annihilations, which is also called the rapid annihilation funnel. And this happens when the mass of the annihilating neutralinos is equal to the mass of the exchanged particle, which could be a light Higgs, a heavy Higgs, pseudoscalar Higgs. The third mechanism is just by having a substantial Higgs-Zeno fraction, which means that it interacts with gauge bosons a lot. OK, so you get this diagram that's very efficient. So here I'm tweaking some have lots of knobs to turn. So I'm turning one of them, the tangent beta knob. And turning the tangent beta knob makes the Stau LSP region huge. It doesn't help very much with the Higgs mass. You can see 120 GeV, but it gives me more dark matter regions. First of all, there's another excluded region up in the left corner where electroweak symmetry breaking isn't obtained. It's remarkable that electroweak symmetry breaking is naturally obtained in most of the MSSM, but it doesn't work out up here. Now, the dark matter regions, we call the focus point this region here, where mu is small, and the lightest supersymmetric particle is Higgsino-like. We also have the rapid annihilation funnel, and now maybe you can see why it's called a funnel, right? But still you have this issue that there's no place in this plane that works out with everything. Okay, so I have another knob, and I'll turn that other knob. And this is basically all the knobs you can turn in the CMSSM. So now when I turn this other knob, which is the trilinear coupling knob, what happens is I can have a stop lightest supersymmetric particle, the scalar partner of the top, still charged, still no good. And you can see that the constraints have moved a little. We still have the LHC constraint here. Beta S gamma has become significant. One good thing is that we have a Higgs mass that is viable in a lot of this plane, but the decay of the B sub S meson to mu mu is happening at a rate that is too large, pretty much everywhere to the left of this 1.5 green contour. So there's nothing really that works here. We've turned all of our knobs. So the CMSSM is great. The parameter space is rich, but it's tractable. The Higgs mass indicates a large ratio, a large trilinear coupling and large M1/2. But basically, that is in conflict with thermally produced neutralino dark matter and B sub S to mu mu. So what are you going to do? You can relax some assumptions. There's some things you don't want to relax to maintain that enough structure in your theory that, that your low-scale constraints work out well. But you can relax just about anything else. So Higgs mass universality, there's no reason why the Higgs masses need to be related to the other scalar masses in the theory. Gaugino mass universality, it's almost an ansatz. And the scale of universality, why do all of the supersymmetric particles have to be universal at exactly the same scale that the gauge couplings unify? Okay, so just to give you an idea of the dimensionality here, the CMSSM is what I would call a 4-dimensional parameter space because there are 4 continuous free parameters. There are lots of models where there are fewer and more free parameters. I'm going to talk primarily actually about a 2-parameter model where I add one more parameter, which makes it a 3-parameter model. And that's sort of the most minimal supergravity model you can think of. The only 2 free parameters here are the universal gaugino mass and the universal scalar mass. Everything is determined by the imposition of strict minimality. Okay, this is a long slide, and I'm going to go way over on time. So I just want to emphasize that what I'm going to be talking about are models where the universality scale is lower than the typical gut scale. And it's been studied what happens when it's higher, too. That's a possibility, but you have to introduce new dynamics there. So here is what happens when the universality scale is lowered from that gut scale. So this is a picture of these mass parameters. So for example, the Beano mass, M1, as a function, this is a low scale mass, but it's as a function of the universality scale. So in the standard gut scale scenario, you live on this axis. And as you lower the universality scale, what happens? The first thing is that this Higgs mixing parameter, mu, becomes really small really quickly. And eventually it becomes so small that it's negative, and then that means that electroweak symmetry breaking doesn't work out. Now, the neutralino LSP starts out, that's this black contour, is the neutralino mass. It starts out tracking the Beano mass. That means that the lightest supersymmetric particle is Beano-like, which is sort of the canonical SUSY standard thing. However, once mu becomes very small, it flips over, and the LSP becomes Higgsino-like, the lightest supersymmetric particle. Okay, and when that happens, you get these enhanced annihilation to gauge bosons, and so the relic abundance plummets. The third thing that happens is that the pseudoscalar Higgs mass, it's just another Higgs boson that we have in supersymmetry, that decreases as you lower the universality scale too. And when when half of the pseudoscalar Higgs mass is equal to the lightest supersymmetric particle mass, right? That is precisely when this diagram, neutralinos annihilating through this pole, becomes super efficient. So that can happen in these models too. It is not typical that all of these things happen in a supersymmetric model. Okay, so standard minimal supergravity is not very interesting, and the only thing that I'll say about this is that this dark blue is still the dark matter, and everywhere sort of in the top part of this plane above this lighter blue contour, there is no good dark matter region. So I'm going to skip through that in the interest of time and get to this picture, which is much better, because now we have dark matter all over the plane. We have a Higgs mass that's in the right range, and our constraints from B physics are way down here, not impinging on anything yet. Okay, so not only do we have regions where the relic abundance is right, we have regions where the relic abundance is too small, which actually leaves open the possibility for another kind of dark matter, right? You could also have axino dark matter, axion dark matter, primordial black holes, who knows? So I've assumed this one particular value, the simplest that I said arose from the simplest Poloni model of minimal supergravity, the absolute simplest thing you could write down. So what happens when we move away from that absolute most simple scenario? So, whoops, I guess that's important. So what I'm doing is I'm picking a point in the plane here, and I'm going to fix everything, except I'm going to allow this value of A naught to change to see how much the phenomenology changes. Okay, so this is changing value of A naught on the x-axis. And on the y-axis, the important things that I'm plotting are the Higgs mass. So clearly, the Higgs mass is too small if A naught is small. So you need A naught big enough to get the Higgs mass large enough. However, this green contour is the branching ratio of beta mu mu relative to the standard model value, and it has to lie in this range. And so if you make A naught too big, then this blows up and you run into that constraint. So what this is telling you is that you have to have an A naught that's large enough to get the Higgs mass right, but small enough to get beta mu mu right. And the one that works out just happens to be that most simple Poloni value of A naught, which is weird, but cool. So here's the summary for this subgut scenario. Basically what I did was I took a model, I fixed A naught where we found that it had to be fixed, and I varied 2 parameters and added this third universality scale thing. And just with a model with really 3 parameters, I found neutralino dark matter with, okay, I can talk about the spectrum of particles, consistent with B physics constraints, consistent with the Higgs mass, everything was good. So people who say that the MSSM is ruled out already, I think are jumping the gun by a long way. There's no general conflict between the LHC results and the minimal supersymmetric standard model, far from it. And even very small deviations from this most constrained scenario, even to smaller numbers of parameters, give really diverse phenomenology that is much different than what you would expect in what we thought, the CMSSM, what we thought was a model that well described the spectrum of possible expectations. Okay, so I guess I want to talk about co-annihilations just for a minute. So co-annihilations were one of those mechanisms that brings the relic abundance down, right? And the reason that co-annihilations happen in these subgut scenarios where the universality scale is different, so I'm plotting lots of different masses here. The black one is still the lightest neutralino. The blue one is the second lightest neutralino. The orange one is the third lightest neutralino. The place where the dark matter is in the right range here happens to work out to the place where all of these masses are more or less degenerate. And so these co-annihilations happen all over the place. And that's really interesting. That's something that's not expected in a lot of models. Now, there is another way that you can have co-annihilations happening. Here it's happening because the lightest supersymmetric particle is becoming Higgsino-like. But you can also have co-annihilations with charginos if the LSP is Wino-like. And I guess briefly, the reason for that is that the neutralino mass matrix is determined primarily by the Bino mass, the Wino mass, and these Higgsino parameters. The charginos are basically the supersymmetric analogs of the charged W boson and the charged Higgs. And so you have the Wino and the Higgsino. So if it's Higgsino-like or Wino-like, you have a large possibility for good co-annihilations. Okay, so this was with Dan Feldman, who was a visiting scholar here a few months ago. We looked at a particular model with non-universal gaugino masses, and that gave us the freedom to have a Wino-like, or have a Wino component for our dark matter. So this was in a gut scale supergravity motivated scenario. Cosmological constraints tell you that the gravitino mass has to be really large, and so that was a motivation for us to put the gravitino mass way up there. And if you're in a supergravity scenario, the gravitino mass and the universal scalar mass are linked. So that means that all of our scalar particles are going to be super heavy. And what we wanted to do was explore basically all of the gut scale gaugino masses that we could and see what kind of phenomenology falls out. So the phenomenologically relevant particles, the supersymmetric particles, the ones that aren't so heavy that we don't care anymore, are the Higgs, of course, right, which actually isn't a supersymmetric particle, but we get the Higgs mass right. The gluinos are very light, and so the LHC can absolutely search for these things. And then the neutralinos and charginos are also roughly at the scale of 100 GeV or 200 GeV. So these are things that could also be searched for at particle colliders. So one interesting thing that we found is if you look at the entire space of models that you could have here, the full parameter space is in gray in this plane. And this plane is the Higgsino fraction versus the Wino fraction. So if the Higgsino fraction is 1, that means there's no Bino component, there is no Wino component. It's all Higgsino. And if it's 100% Bino, then both of these fractions would be 0. Okay, so just requiring that there's the right amount of dark matter excludes all of the gray area. Requiring that it has not already been seen at a direct detection experiment, which nothing has been seen at a direct detection experiment, excludes this blue stuff. And what you're left with is these red points. Those are the only models that are phenomenologically viable anymore. And bizarrely, they all lie on basically a straight line. This black line is the Higgsino fraction exactly equal to the Wino fraction. It's a bizarre thing that happens to happen. And so then we look at what can you see in these models? How would I know that we've discovered this model? And so we looked at the direct detection prospects and the indirect detection prospects. And for direct detection, this is that spin-independent scattering cross-section as a function of neutralino mass. And you asked earlier, why are they all, we were looking at a place up here at low neutralino masses or at low WIMP masses. And now I'm showing you sort of more fully what the parameter space is. This is the current constraint from Xenon 100, so it does exclude some of our models, as I showed you before. And this is the projection for Xenon 1 ton. This is a 1 ton of Xenon experiment that is built, and I think they're going to fill it with Xenon fairly shortly. So the Xenon 1 ton could exclude all of these models that have small mu, which we would say that means they're natural in some sense. So great prospects for direct detection. The other thing that the shading here is telling you is the gluino mass. So basically, the lightest gluinos will be probed by both direct detection, and they're the easiest to produce at the Large Hadron Collider. So if you see direct detection and a light gluino, this is a good bet, and then you can go out and look for other signatures. We won't see any of the photon signals from these anytime soon. But what's indicated in color here is the neutralino chargino mass degeneracy. And these, so basically the difference between the neutralino and chargino mass is like 10, 20, 30 GeV, which is a very small mass splitting. And the reason that that's problematic is because if you produce 2 charginos at the LHC and then they decay into stuff, the stuff at the end of the day, if this mass splitting is small and a chargino decays to a neutralino, the stuff, the rest of the stuff that comes out is going to have hardly any energy. So it's really hard to see these models where this degeneracy is so small. So even though the other particles here, the neutralinos and charginos, are really light, you're not going to see them at the LHC, but you might see them at a linear collider. OK, so I talked about co-annihilations in 2 different ways. Now I just want to talk about pole annihilations very quickly. So basically, since this is a general thing about the MSSM, and actually it's even more general than that. Since it's a general thing about the MSSM, you want to investigate sort of each of these avenues, right? What are the generic features of each of these avenues? And pole annihilations are interesting because you can characterize the relevant features of the model with a small number of parameters itself. OK, so this was work that I did with Chris Kelso, and this is us actually visiting the Homestake mine where the Lux dark matter detector is located. We actually got to go down and see the detector, which was really cool. So the question that we wanted to ask here is, if the dark matter abundance is achieved through a resonance, which is basically this annihilation through some S-channel pole, how small could the spin-independent scattering cross-section be? When will we see this in direct detection experiments? Or is there a time when we will say we have completely exhausted this type of model? You will no longer expect to see these resonance models in a direct detection experiment. And so in the interest of time, I'm not going to go through too many of the details here, but this is the spin-independent scattering cross-section as a function of the Beano mass. And here, the lightest neutralino is pretty much Beano-like. And so you can see when twice the mass of the dark matter of the Beano is equal to the mediating pseudoscalar Higgs, 200 GeV, you get a huge decrease in the spin-independent scattering cross-section. Now, this is the limit, the current limit from Xenon 100. Everything above that line is excluded. And as these direct detection experiments get better, this line is going to move down. And so eventually, we're going to be in the situation where we're sitting at the bottom of this point, which means that one might say that the dark matter is really tuned. There's not really a reason why it should have exactly half the mass of the pseudoscalar Higgs, right? So we basically went through all this parameter space. And what we found was that in all of parameter space, these cross sections at the bottom of this funnel are detectable on approximately a decade time scale. So if you look at the projected sensitivities for future experiments, these above in this upper left quadrant, these are experiments that are currently running and limits that currently exist. And these are projected sensitivities. We actually were a little bit less optimistic than this for our projected sensitivities. And what we found is that the required tuning decreases dramatically over the next decade, to the extent that within about, I think I wrote it here, at this rate of progress, within about 12 years, direct detection experiments will be able to completely close this funnel region. So that's important for all MSSM models. OK, the very last thing is some work that we did on what's coming next in direct detection. And what I've talked about so far are zero background experiments, basically. But there's one really important not zero background experiment that has, for 15 years now, observed a modulating signal that they attribute to WIMP dark matter in their detector. And so the idea here is we live in the Milky Way galaxy, where there's this big cloud of WIMPs around us, or cloud of dark matter. And that cloud is sort of stationary with respect to the galactic frame. Now, we're in our solar system flying, rotating around the galactic center, right? So our solar system is going into a wind of WIMPs, you can think of it as. And furthermore, within our solar system, the Earth is moving around the sun. So sometimes the Earth is moving in June, the Earth is moving in the same direction that the solar system, or has a component of motion along the same direction that the solar system is moving around the galactic center. And in December, it's moving against that component. So in June, we're moving faster through the WIMP wind, and in December, we're moving slower, which means that the event rate in June should be high, and the event rate in December should be low. And so this is what they claim that they are measuring here. Clearly they're measuring some kind of modulation. It's not totally clear that it's WIMPs yet. And the reason that it's not totally clear that it's WIMPs is because if you look at these exclusion contours, everything above these contours diagonal here is excluded. And you can see the DAMA regions lie well within almost all of those contours. So I would say that's more decidedly excluded than, say, the CDMS blue region here, which is on the edge. Oh, and I should point out that this blob was discovered by Paolo. Okay, so the question that we wanted to answer had to do with what's happening now at DAMA. So DAMA currently has lowered the threshold of their detectors. You saw actually before, this was listed as the 2 to 6 keV, or in the 2 to 6 keV energy window, and they're going down to 1 keV. So what can they say with 1 keV? So right here, this is the modulation amplitude as a function of energy, right? So currently they go down to 2, and that's all of these gray bins are the old data that you saw in the previous plot. And there are a variety of dark matter models that are compatible with that old data. So basically, all of these curves here are compatible with the old data. And some of these are 70 GeV dark matter. Some of these are 10 GeV dark matter. And so the question is, if they open up 2 more energy bins, will they be able to make a statement about one way or the other? Is it high mass dark matter, which is pretty definitely excluded? Is it low mass dark matter, and what the deal is? So we did this analysis. Chris Kelso and Chris Savage did this analysis, and this is just one of the plots from the paper. Basically, this is what they would see in the 1.5 to 2 keV energy bin, and what they could see in the 1 to 1.5 keV energy bin. And so basically, their measurement is going to be a point somewhere in this plane. And what you see is that not a whole lot of the plane is compatible with both the high mass explanation and the low mass explanation. So basically, whatever they measure is going to make a statement about whether it is 70 GeV dark matter or 10 GeV dark matter. And so that's really good news. At least they'll break the degeneracy of explanations for their own modulation signal. OK, so looking ahead, there's a ton happening in direct dark matter searches. They're pushing the thresholds down to eventually we're going to get to the irreducible neutrino background, which then we'll really be doing neutrino physics, but it's still going to be interesting. And also directional searches, which I told you about, DAMA looks for modulation, but if you knew what direction those WIMPs were coming from, that would also really help, right? Also, indirect dark matter searches, AMS2 has a lot more stuff that they're going to release, and that'll help us nail down some of the cosmic ray propagation parameters to take some of the guesswork out of exactly what the astrophysical backgrounds are and what the propagation model is, as well as Fermi and more Cherenkov telescopes like CTA, et cetera, and Veritas's upgrade. From the LHC is currently shut down, and when it turns on again, it's going to be at 13 or 14 TeV. And so that's super exciting, because then 2 TeV gluinos should come flying out, and we will have discovered something. But who knows? Right now, we wait. And also, the prospects for a linear collider, there were a couple things that I showed you that would be screaming signals at a linear collider. It looks like there's a linear collider that will probably be built in Japan. And that will certainly study the Higgs properties in detail, which will be very helpful. And it may also discover some of those light electroweakinos if those things exist. And CERN's plan for a linear collider, it's called I forget what the first C is now. Anyway, there's another plan for a linear collider called CLIC that's operating energy is currently listed at 3 TeV, which center of mass energy, which basically that means they can make anything up to 3 TeV, which is fantastic. So from the theory side, what I am spending my time on is what is left in supersymmetry. And as you can see, I think there's quite a lot there, and there's a very interesting phenomenology. And the other question is, when will we know that we've covered it? So some of the things I'm thinking about are different types of minimal models that are still viable and still desirable for one reason or another. non-neutralino dark matter, there are plenty of options there. And also more novel dark matter models, maybe something different than the standard SUSY neutralino. This is an interesting question because the tools do not exist to fully analyze the compatibility of these new models with experimental results. All experimental results report their results basically assuming a WIMP dark matter model with a standard halo model. And so thinking about how to look at these models in more detail is really important too. And I'm sorry that I went over on time, but I just have one more slide because this is another thing that's taking up a ridiculous amount of my time. The Rocky Mountain Conference for Undergraduate Women in Physics is being hosted by the University of Utah. This is going to be January 17th to 19th. The states that are shaded in cyan here are our regions. So undergraduate women in physics are going to be coming from all of those states here to the University of Utah for Martin Luther King Jr. weekend. And it's very exciting. Our webpage, I've been told, is finally up. And encourage your students to apply. And those of you who are in the audience, apply. All applications have to go through the APS. We vet the applications locally, but even local students need to apply. So please tell everybody to apply. Thank you.
So, suppose you succeeded in detecting a WIMP particle,
Yeah.
and then you measured its mass and cross-section. To make a case that it's a dark matter particle, you would have to prove that such a particle exists with density comparable with what you need.
Yes.
But isn't it a hopeless task?
No, you can do that at the LHC. You can do it at the LHC, and if you measure if a direct detection experiment measures something, you'll have at least an indication that the mass is probably in a range that the LHC has a hope of measuring it, or some future collider.
Let's say the mass is 10 GeV.
10 GeV.
Well,
that's small, but okay.
Right? Oh. That would make it more favorable, right? Because then the density would have to be higher.
Yeah.
So for 10 GeV, what would the density? What density would you need to account for astronomical measurements?
So so the thing that's measured astronomically is just the mass density, right? So it
Yes.
scales.
So
It's just proportional.
You know the mass density. Now you know supposedly the mass of the WIMP particle.
Right.
So what would the density be? I don't know.
So the canonical number is 0.3 GeV per cubic centimeter.
Okay,
So scale that appropriately with.
Particles per cubic meter.
Huh? So for a 100 GeV particle, it's one in your coffee cup. So this is, one in this big.
Okay, so it's a pretty high density.
Yeah, it's a pretty high density.
And then what would be the measurement of that density?
So what's that?
So my point is you measure the particle to have some mass.
Yeah.
Now you need to show that you have exactly
Well,
one particle per cup.
There are a couple things you need to show, right? It's not only that you have to show that the mass density is correct. You also need to show what the annihilation rate is, right? So you need to connect the particle physics properties.
Well, the first one I'll define with the second one.
Right. So
So how do you prove that there is exactly one
Right.
particle per cup in the universe?
You-
What measurement would
it's a suite of measurements because, excuse me, you need to nail down what the halo model is. You need to know not only how many, sorry.
That's a dark matter particle.
Yes, it got me. Yeah, no, it's true. Just seeing it in a direct detection experiment is not enough. The best way to find out if that is the only thing that makes up the dark matter is to measure its annihilation cross-section, which there are some ways you can do it in a collider. Also, indirectly detecting it, you can't be 100% sure, but if you indirectly detect something that has the right annihilation rate and the right density of things to be making that signal, and you see it in a direct detection experiment, I think we can be reasonably sure that we've discovered dark matter.
What sort of explanation could there be that some sort of dark matter particle or matter particles or whatever wouldn't be swept up over 14 billion years by the existing matter that we do see?
Swept up. It's different stuff.
Well, I mean,
I don't know what you mean by swept up, but it's different stuff.
There's planets and stars orbiting galaxies. What sort of explanation could there be that matter wouldn't attract that mass and collect it and not release it again.
No, it all interacts gravitationally. So the distribution of stuff is what it should be if it all interacted gravitationally together. You may be worried about black holes, but yeah, the difference is that standard model stuff, gas, whatnot, atoms, can scatter on each other and lose energy efficiently, and dark matter doesn't. So, so the distribution of the dark matter that we see is in agreement with that sort of perspective on what it's made of and how it interacts gravitationally, and the non-gravitational interactions that contribute significantly. So I think the thing that you're concerned about is worked out. Other questions?
So just the bullet cluster?
Yeah.
So I'd always thought that the gas, that you only saw the gas because it had been heated by the shock, the collision between the two clusters. But my question is, how much of that signal that you see
Yeah.
is because it's hot? Because
Versus how much is just because it's gas?
Just being hot because it's heated by the clusters.
I think people use Chandra to map the gas in clusters in general. So, and Kyle's nodding his head. So I'm pretty sure that they would see that. I mean, it's hot in the sense that it is hotter than the dark matter particles, maybe. I don't know. Why do you call it hot gas?
It's a million degrees. It's a million degrees.
So it's hot.
But it's hot.
That's hot to
not
us.
because it's not hot because of the collision.
No, yeah.
That would be quite a pleasure.
It's hot because of gravitational effects. So it's just naturally associated with the clusters themselves.
Yeah.
And all you're seeing is the shock in terms of it affects the distribution.
Yeah, and there's some actual, it's not really clear whether that really is a shock either. My understanding is that people are still arguing about like whether that's a coincidence or whether it really is a shock.
I have a completely stupid question. So the candidate you're looking for is a weakly interacting particle. Is it possible that it's a non-interacting particle?
Oh, yeah.
Interacting via gravitational force?
Yeah, we call those gravitinos. No, then yeah, that's totally true. Or it could be primordial black holes, in which case we will not see them in any of these ways.
So this is the possibility that is not very interesting.
Well, yeah, so there are a lot of constraints on gravitino cosmology because it's difficult to get lots of other stuff to work out correctly if gravitinos are the dark matter. And similarly, primordial black holes, which are the other main thing that would be not interacting except for gravitationally, there aren't really any good models for how they're created in the early universe. Like, why would they be there? And here we have an excellent reason why these things would be here. So it's not that those other things couldn't be the explanation. It's just that, I mean, first of all, it's very difficult to, I have no idea how you would search for them, so you'd kind of be giving up. But also, there aren't really fantastic models for why the universe is the way it is.
So with the Dama modulation,
Yeah.
it looks like it's in all the plots, it's clearly excluded by all the other experiments.
Yeah.
It's been like 15 years or something, right, or 10 years or something, and no one's come up with an explanation as far as I know for why they're seeing modulation.
Yeah.
Is there a way that you can, is there something that's not shown in that plane that allows you to resolve those measurements?
No.
No. Okay, so those are just completely intentional.
Yeah, people have proposed many, many explanations for what the modulation signal is, and the Dama collaboration has said all of those explanations we have thought of, and that is not the explanation. I will say that they don't release their actual data, so we trust them that those data points that are there are the way they should be. But apart from that, we don't know. So there's a modulating background of muons, just due to the due to the solar cycle and other reasons. But there's a modulating background of muons, but the phase is off and it's just not quite right. And so for a while, people thought that might be the explanation, but nobody knows.
So you are planning to have a copy of Dama experiment in the
Yes.
southern hemisphere?
That's why I mentioned that thing about the northern hemisphere. So if there were an experiment in the southern hemisphere, then because of the motion of the Earth through this thing, their modulation should be reversed from the phase that the Dama modulation is. So it's really important to do this in the southern hemisphere, and it's being done. There are a few complications. One is that Dama uses these very pure sodium iodide crystals, and they've made some kind of deal with the devil where this company that makes those sodium iodide crystals won't give them to anybody else, and who knows. So it's very difficult to actually repeat this experiment in the southern hemisphere, but they're trying to do it. And so, they put the test module together really quickly, from funding to launch, I think was 3 months, and then they deployed it in the ice. And it's been down there for a year and a half or 2 years now. And so they're taking data, but it's not pure enough. So they need the next, like the experiment grade experiment to go down. And hopefully they'll see a modulation and it'll be phase reversed. And then we'll wonder why all those other experiments didn't see anything.
Any more questions? Yeah. Last one.
I have two questions. First one is only curiosity. In your slides about the M supra,
Mm-hmm.
there is a relation which looks very strange to me. That's the Plony relation
Yeah.
in zero. So it's 3 minus.
3 minus root 3.
Do you remember what kind of mechanism to give such
Yeah.
relation, or
No, it's just the mechanics of the scalar potential. So if you write down the absolute minimal scalar potential, where basically you only have one term to describe everything, that 3 minus root 3 falls out of it. So it comes from a mathematical place.
the second question is about the dark matter wind or wind.
Yeah.
Wind. Of course, on the whole, we think in a halo, it should be at rest. But still, it's possible that locally, for example, we know that our Milky Way has some satellite,
Mm-hmm.
satellite galaxy. Some satellite galaxy actually move towards the sun in some sense. So
Yeah.
such motions would bring some, local winds.
Mm-hmm.
It's different from the
Yeah, so those go under the name of dark matter streams usually. Yeah, so we could be riding in a stream of dark matter and it would completely change everything. And that was actually, I think those were suggested.
Yeah. Would that affect the Dhamma?
Yes, this was suggested as an explanation for Dhamma. And maybe you know, Chris, I think it's now incompatible with the other experimental results, but I'm not totally sure what the status of streams is.
Yeah, so it depends somewhat on the density that you assume for the stream, but if you take sort of reasonable values based off of simulations of our galaxy formation, then the streams should be relatively rare, and you wouldn't necessarily expect them to be the dominant component in a signal that you would measure. So then they're not going to be the thing that you would expect to be causing Dhamma necessarily.
Okay, let's thank for